Okay, I think we are streaming. How do I check? All right. Okay. Wait. How do? All right, am I on Twitch? Okay, cool. So it's 4 o'clock. We're almost 5. Today, I'm gonna be doing some basic OpenCL work, hopefully, but also going over my notes and readings that I've been doing this past week on how GPUs work. Second set of coffee today. Yeah, we'll do this until I get hungry and have to cook dinner. All right. So in my last stream, I finished work on a basic CPU core, and I went over some things about the differences between CPUs, GPUs, and somewhat, or a little bit about TPUs. So there's lots of terminology when it comes to GPUs, and also, like I said, I am a noob, right? So this is just everything I've compiled in the past week. My goal eventually is to make a GPU core like I did in Verilog with a CPU, just for fun. So, okay, there's lots of terminology, and I think it'd be easiest to start with that. Okay, so let's do NVIDIA. All right. Actually, before we go into terminology, let's just go over something, just in case people like me are like confused. Okay, so what do GPUs do? What do GPUs do? So GPUs process multiple data streams simultaneously, so and have good throughput. So basically, they can execute a bunch of data streams or process them through multiple lanes, which we'll get into later on, and they can execute all these at once or in lockstep, and they can do up to, well, depending on what architecture is used, hundreds or thousands at a time or every clock cycle. So that's incredible, right? Obviously. GPUs process multiple data streams at a time. They have lower clock speeds than CPUs. And they have higher memory bandwidth than CPUs, optimized for throughput. So what I mean by this is that if you look at a general layout of what a CPU looks like versus a GPU, you'll see that CPUs have a bunch of large caches, some within their cores, and then some of and then usually an L2 cache or L3 cache on the CPU. Maybe see if I can pull up a photo. This is a pretty good photo of it, of what I mean by caches. CPUs provide low latency for serial instructions, and then GPUs execute similar commands in parallel for higher throughput. Yep, L1 cache. Okay. let's see what else. Okay. So let's go with SIMD. All right, so this is the basic paradigm or concept that comes with parallel programming in GPUs. So we have two different concepts here that sound very similar, SIMD and SIMT. SIMT. What the hell? What is this? SIMT. Threads are explicitly defined by a programmer. You can see thread ID and are aware of the thread unit of execution. Lanes are implicit, are built into GPU hardware. All right, so when you start a parallel program, and we'll go into this more later on, there's this idea of executing or launching multiple threads, and you can think of a thread as just a the simplest unit of execution in a program, right? And so if we have something basic like C sub I is equal to A sub I plus B sub I, which is like vector addition, you can think of that kernel as a C function which adds all the A's with all the B's and puts that result into the C vector. And for each element, you essentially are launching a thread to compute the addition for each pair in the A and B vectors. And so you can think of that as thread, and these threads are separate units that have to be executed. And these units, how are they being executed? They're implemented directly in the hardware. So if you look into a GPU hardware, let's say, just a lot of my reading came from the GCN architecture by AMD, GCN 1, which is like the simplest one like I could find online. There are basically a lot of these things called SIMD units, and these SIMD units have a vector ALU, which you can think of as just like multiple ALUs, and each of these ALUs are doing that addition for each of those elements. And so this is what I mean by that. I'm pretty sure there's a lot more about this. I'm still like a bit fuzzy on the real difference between this. I mean, it seems like it's kind of abstract, you know, like the whole SIMTs are explicit, defined by the programmer, and SIMDs are you don't really think about it when you're programming. You're just expecting that this is how your threads or your kernel is executed by the GPU in parallel. Wait. Why is this? Okay. All right, moving on. So that's important to know. Let's put that here. All right. Now this is where it starts to get perhaps a bit confusing. We're gonna break down each part of the, let's say, a basic kernel execution timeline into the components that are seen in GPUs. Let's start with what we mentioned earlier, threads. You know what? We have threads / work item. Thread / work item. Oh God, I hate. Thread / work item. Then we have thread block. Is it thread blocks? / work group. A and B. And then we have warp and wavefront. Warp / wavefront. And then we have streaming multi-processor SM. Compute unit. I think this is the most important part, but we'll get into that later. And then we have I think that's pretty much the most important things to know. Let's start with kernel. Actually, no kernel. Okay. Like I mentioned earlier, kernel, think C functions. Okay. They are the things that you want, the thing that you want to do in parallel, basically. All right. Unit of a code program. Unit that is called once and returned once, but executed many times over the multiple threads. Over multiple threads. Okay. The simplest unit of execution. Think of vector addition C equals to A sub I plus B sub I. Each addition can be seen as a thread. Where NOOB instructions in a thread. For example, okay, for example, let's do this. Let's do, where's my thing? For the given addition, vector 2 leaves vector 0 and vector 1 on store restore into vector 2 follows store vector 2 into memory. There we go. Alright. 1, 2, 3, 4. Hope that makes sense. Thread block or work groups. Alright. Alright, what's the best way to do this? This is the smallest unit of thread exposed to programs. Okay. Each block is assigned to a sharing multiprocessor or compute unit and it can okay. This is too much. Okay, block is composed of how do you spell arbitrarily size? Typically multiples of the warp size, which we'll get into next. Alright. Sorry, I'm like typing at the rate I'm thinking in a way, and it's easier to type than to speak. Alright, if it's not obvious already, everything on the left is NVIDIA terminology, everything on the right is AMD terminology. Warps and wavefronts, alright. Each thread block, okay. Thread block is composed of warps or wavefronts. Other groups of threads which can be executed in a lockstep. Okay. GPUs. Warp, okay. Wavefront size is 64 threads. At least for most, I think. Even the modern ones might. Which one is it? AMD GPUs. AMD warp sizes. Yeah. Alright, 064, 64, 64. Yeah, that's right. That's right. Okay. All threads. Are scheduled onto a single J-Mult processor or compute unit. Okay, I'm just gonna start using warps because the results of the execution of a wavefront, warp or wavefront like that, may usually do not occur in a single clock cycle. Again, I'll go into that later, but you see, simple addition already probably takes at least 4 clock cycles. Okay, now this is another important concept here. Oh, there you go. That's how you do it. All right. Hiding. Okay, this is more of the implementation thing. Hiding memory latency. actually need to read more on hiding memory latency. I'm pretty sure this is like incredibly important concept, but I'm not gonna be implementing it for my GPU architecture in Verilog because honestly that sounds quite. It's like an implementation feature that isn't too necessary. I'm just trying to understand how units of execution can be processed simultaneously, and how memory bandwidth um, affects the speed of that thing happening. And doing something like this and trying to make reduce memory latency or hiding it is just an additional step that I could do. It's just I don't think it's necessary for my goal. So I'm pretty sure this is how it works. So every compute unit, I'm just gonna stick with AMD terminology. Every compute unit is composed of thread blocks that are assigned to it, and so inside that compute unit, it divvies it up into warps, which is just another group of threads that it divides from those thread blocks. I think it'd be easier to show. Nope. Nope. Okay, someone does this right. So what you're seeing here is you can think of as, this is actually like kind of terrible. 6 cores belong to only one compute unit. I don't like how this is using it. Okay, all right. So we have a compute unit here. It has up to 4 SIMD units, and so you can think about it like this compute unit is gonna have a bunch of thread blocks, and those thread blocks are gonna be broken up into warps, and those warps are scheduled or issued to these SIMD units in round robin fashion. If that SIMD unit is available or can process something, it's assigned a warp or a wavefront. There can only be one issued every clock cycle, up to one issued every clock cycle. So let's say, let's say we start processing something in this compute unit, okay? Clock cycle 0, for example, and this is just a complete basic timeline. On clock cycle 0, there's available wavefronts here. It checks SIMD 0, is that open? And then it gives it to SIMD 0. And the next clock cycle, if it has another wavefront available and SIMD 1 is available, then it gives that wavefront as SIMD 1. And then they each process them, in their own. Alright, now this is the big dog. I'm gonna get water. Yeah, I know it's such an informal video, but this is why it's so fun. I can do whatever I want. I don't have to make this look so clean, you know? All right. The heart of GPUs contains I don't actually know what NVIDIA calls it. I know AMD just calls them SIMD units. And do I not have any notes on that? There's no way. Whatever. Contains SIMD units. Wave front. Okay. Plus other important others like other like cache, and honestly it's not really important. Scalar units, etc. But those are not important for purposes. All right, so this is, you can think of as perhaps the lowest processing component of a GPU, besides the actual SIMD units themselves, which process multiple data elements at once. All right, so these compute units are what hold the multiple SIMD units that each process their own warps, and so this is where all the power of parallelism comes from. All right, let's give an example because I think honestly that would clear things up. Man, this is so...
I don't love...
Wow.
I don't love...
Man, can I just do like... Ugh, I guess I'll do that. Bro, I don't even know. Okay. I hate having to keep switching between NVIDIA AMD terminology. Like, this is such a gatekeepy. I know it's probably because I don't know. I have no clue why they do it like this. They're all the same things. There's just different names for it. Yeah, that's really stupid. But yeah. To each in the unit, a wavefront is dispatched to each in the unit inside the what is the SM or compute inside. Okay, within a block, threads are grouped into wavefronts. AMD. GCN1, it's 64 threads. Is this processing? How do I make this like fucking? Oh, I hate down, bro. All right, and then this is wrong actually. Oh, I should start. That's my two. Okay. like that. This isn't really. Oh, that's okay. Let's think. Global. DRAM. By the way, I found some GPU examples, like really simple ones, on GitHub, and also this is somewhat based off that, and there's also just some of my reading about the GCN1 architecture by AMD. I'm not gonna go into addressability yet, like how many bits there are and all of that yet. Yeah, I'm gonna show this in a block diagram. Maybe not today, but this is just laying out the foundation of what I'm thinking in my head for my NOOB GPU architecture. GPU. Scheduler. I'm also going to be using AMD terminology more because this compute unit just sounds cooler or nicer and easier than streaming multi-processor. And also because I want to like AMD for many reasons. Gotta go for the noobs, man. Not the noobs, but like underdogs. You gotta believe. Blocks that can be launched. As many as needed for the kernel workload. Queued, if that's spelled that right, queued. CUs are taken up. Doesn't matter. I mean, L2 cache. I just call it cache. Like NOOB GPU. Tiny GPU does that. Frequently used data by multiple. Once data is fetched, store it on your device. GPU. More quickly. Only requests. And then we have our memory controller. And cache. I don't even know if I want cache, honestly. A cluster 54 compute extra cache. I don't like this. Okay, this thing is bothering me. I thought I got this. That is crap. That is so. Guys, don't. Okay. Let's just do program counter. Okay. has 10 instruction bar. So an instruction buffer can have up to 10 wavefronts. Honestly, for mine, I'm probably just gonna do one because whatever. And I can do a program counter for that. For that wavefront. Program counter for that wavefront. And the corresponding instructions. Okay. I don't think an instruction cache is necessary because that's just overkill, man. Instruction buffer. Store one wavefront. Oh no, but that kills the whole. Yeah, whatever. I get it. I get it. Wavefront scheduler. So it comes with an instruction, right? These wavefronts just come with one instruction, with multiple instructions, really. But okay. Okay, that makes sense. Mm-hmm. Damn, that's insane. Just thinking about how I would even program this, but so you would have to have, what is it called? This kind of wavefront. You have to have a wavefront, and then that wavefront has a bunch of instructions in there, right? So, like, yeah, this is, fuck. I don't really like this. Core state. program memory. I don't like that. All right. Let's see. I'm gonna save this. All right. Do I really need cache? Honestly, mobile data, okay. Scheduler, blocks can be launched, alright. Alright. Just making sure. I mean, I can honestly start working more on this when I actually start implementing it. I don't know if I like this, you know? Raise the next instruction. Okay, only one instruction at a time. One instruction per wavefront may be issued. The warp scheduler issues a warp to one of the SIMD units. So they have to correspond, right? I mean, how do I even do that in Verilog, bro? I'm gonna do something with cache, but like, oh, that'd be a pain in the ass. Okay. All right, moving on. Move on. All right. All right. Let's do some OpenCL stuff. Hands-on OpenCL for fun. This is so fun. All right. Let's see how far we get. Setting up OpenCL. I did that already. Overview. I guess that might be cool to read. Important. Okay. Blah 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 blah. Matrix. Ooh wow. Matrix mall. Okay. This was a pain in the ass to do, by the way. Like, I don't want to do this again. I'm probably gonna have to in the future, but I don't. God, yeah, this is all pain in the ass. Pi OpenCL. Make sure you have Python installed. Install NumPy. Download the latest version. Maybe I should consider Linux, huh? Oh, 10 cores. Microprocessor trends. What is this? Overview, OpenCL. DSP. Right, single portable program uses. Many core challenge. How are we to build a software ecosystem for the heterogeneous many core platform? Image processors have many possibly heterogeneous cores. 32 wide SIMD, 16 wide SIMD, 16 wide SIMD, 61 cores. Okay. Increasingly general graphics APIs. Okay. OpenMP. Okay. Open royalty free center for. Okay. Yep. Origins. AMD merging data commonality across products. NVIDIA GPU winner wants to steal market share from CPU. Wrote a rough draft Strawman API. Kronos Compute Group formed. Then bam, this guy came out like a baby. CPU winner wants to steal market share from GPU. Oh, Intel. Poor Intel. The story of Intel. It's so sad. Intel. What happened to you, Intel? Wait. What happened to Intel, bro? Oh my god, Intel. Oh my goodness. Intel. Oh, is there any hope for Intel? I don't know. Push vendors to standardize. Okay. Compute unit. Oh my god, I hate these words, man. The host. One host and one or more OpenCL devices of one or more computing divided into processing elements. Memory is divided into host memory and device memory. Okay. Treated as one OpenCL device. Each GPU is a separate OpenCL device. Can use GPU and non-GPU. Will always have to be its own host. NPEs per CU. Yup. Each GPU is a separate OpenCL device. Can use CPU and all GPU concurrently through OpenCL. You can run a OpenCL program. I hope I can. Procedure. Take the provided device info program, inspect it, and edit a virtual voice. Build the program. Where is it? How do I do that? Oh, then you look at the GitHub. Noob. I am a noob. See. Device info. This looks like a lot. I don't like how many includes there are. Noob kernel. You see this? That's from Perplexity. Super noob. CL dot. Oh. You know what? All right. Honestly, just do this. Error code. Please update your include path. Oh, God, do I have to download that? Oh, please tell me I don't have to. Error. Oh my God. Bro, I don't want to do that. I do not want to do that. Error. Can I just delete all these errors? Error. Oh my god. Oh my goodness. Check error. Oh no. Check error. Is it because, oh my god. I don't want to do that. Please. Please, this is NOOB exercise 0. Error code.h. I don't like this already. I do not like this stuff already. OpenCL. Man. If, well, we're not, so we're just gonna do error code.h. Nope, wrong one, I forgot. Error. Let's hope this shit works. Control. That's good. This is good. Okay, this is good. NOOB. Oh, yes. Let's go. Version open. Okay. Platform AMD. Vendor AMD. Number of devices. Open 6 compute units. Local memory size. Global memory size. This is sick, man. Maximum work group. That's how many what is it? Blocks we can have. 256 max work group. So 10, 24, 10, 20. Oh, that's cool. This is, see, man, that's sick. Max compute units. I'm actually curious. Max compute units. Size of this thing. Get device, OpenCL version. Damn. Version. That's cool. Okay. Getting device local memory size. You know what? What does this even do? Error in. Oh, man. Look at this C code. Isn't that beautiful? And look at this case statement, bro. This is like, oh my goodness. Error code. Man. Error during operation and line this. Damn. This is like if else crap, you know? Prime number. Ah, beautiful. Memory size divided by 1024. Terrible. That's terrible code. T1024. Guys, no magic numbers, man. You're not supposed to do this. Is it because 1024 is like, I think that's number of, what is it, number of, I don't even know. The maximum size of dims, size T dims sims. Wow. Dims, get the maximum of the work groups, number of dimensions, number. Wow, man. Compute units. Dimensions for each of these. That's incredible. That's incredible. You know what? No more. Don't let me import anything else, man. I don't want any more shit. Oh, man. The big idea. Replace loops with functions. Process a 1024 image. Yeah. That looks bad. I agree. Floats. Not good, not good. Instead, we do kernels. And it's just one thread, or global IDs, okay. ID, like global ID of this. Damn, that's good. Good job. Global dimensions. Okay, actually, yeah, this is probably really interesting. I mean, useful. We're gonna do some noob shit. Sorry, do I need this? Yep. Sorry, I need to take notes, man. Jeez. All right. An n-dimensional domain of work items. Global dimensions. The whole problem space. For example, 1024 image space. Local dimensions. Work group. Or thread block. I think that's thread block, right? That's the same thing. Yeah, thread block. Wait. Yep. That executes together. Example. 64 by 64 section of the image space. They are best for your algorithm. Synchronization between work items, possibly within work items. Yes, we know that. We went over that earlier. They cannot synchronize between work groups. Okay, we know that. This makes sense. OpenCL and dimensional range, ND range. Number of work items in a work group is called the local size. Number of work items within a work group. Or you can choose a work group size for you. Yeah, that's bad. It's called the local size or the work group size. Are grouped into work groups. Can share local memory, and okay, we know that. Okay, this is some like. Okay, this is good stuff. Private memory per thread. Local memory was a per work group. Shared memory. This is good, important stuff to remember, man. Global memory is obviously on device, visible to all work groups. So you can think of like top layer. Visible to all work groups. Work group grid. Host memory on the CPU. Oh wow, okay. On the CPU. Wow, this is some noob shit. Memory. Whoa. did I just, damn, okay. Dimensions. You are responsible for managing data between global, host, global, local, and back. Private memory. Again, I don't know if I spelled that, but whatever. Then which kernels execute and which synchronization and memory management is defined? Which kernels execute? Okay, that's like kind of vague, but I'm in which kernels execute. Yo, my fucking laptop, it feels hot. Oh, God. Google Chrome, man. Google Chrome is a beast, bro. Points to a single device. To a single device within a context. That makes sense, okay? So if you have the whole like program, and in that program, you have you could have a lot of devices with their corresponding device memory, and then you can write commands for each of those devices, and those commands get entered through a queue for that device. All right, cool. For each point in the domain, kernel void times 2, okay. Execution model defines a problem domain and execute an instance of a kernel for each point in the domain. Int I is equal to get global ID, and the output is just multiplied by 2 for the I. Okay. Yeah, what is this 10 for? What am I reading 10 here for? 0, 1, 2, 3, 4, 5, 6, 7. Why did you do 10? What the fuck is 10? 10? What? Why'd you write 10? Oh, okay. Define a problem domain, execute an instance of a kernel for each point in the domain. An instance of a kernel. Float input and output. Okay, yep, yeah. Now we know this global memory now. This is okay. Get that global ID for this kernel. I'm assuming. I don't really understand that yet. And we have an output I and an input I. Why is it 10? Why is it doing 10? Oh, is it just an example? 10 becomes 20? Horizontal reflection? Damn, bro. That's some crazy stuff that I don't understand either. That's some like open like okay. Man, graphics people are crazy, bro. Look at this. Okay, IDs for the X and Y coordinates. Get image width. Okay, sure. Image 2D. Write only image 2D, okay. The source value is read the image, whatever that means, with X and Y, write image. Compile for GPU code. Compile for CPU code with source. Vector addition. Our lovely, beautiful vector addition. Hello world program of data. Let's add 2 vectors. Well, hey man, I'm a noob, okay? So teach me. Vector addition. Kernel. Oh, there we go. This is the fun shit. Okay, yeah. NOOB addition. The vector NOOB. The host program is the code that runs on the host. Okay. Set environment. 5 simple steps in a basic host program. NOOB program. NOOB host program. Basic steps for host program. Well, what do you think a host program is? Code that runs on the host to manage kernels and environment for the OpenCL program. Yeah, no shit, okay? Step 1, define the platforms. Step 2, this is honestly a pretty good slides, man. Devices, context, queues. That's like, it's like reading a book, but simple. And build the program, okay? Dynamic library for kernels. Set up memory objects. Yeah, that sounds hard. Define the kernel. Wow, we're only defining the kernel at step 4. Attach args to kernel function. Just let me get user reference card, how to pull information. Oh, I don't like that either. Submit commands, submit. All right. Command keys, okay. Compile the code, all right, cool, kernel stuff. Okay. Remember, context, environment within which everything's basically happening, okay. Okay. Good. Grab the first available platform. Oh my god. I have to use this shit. The card shit. Where's the card shit? Oh my goodness. Oh, God. No, man. No, don't know you do that shit, man. Look at this. All right, let's not complain though, right? Can we just? Okay, all right. Command queues, context, querying. Okay, good. Shit, I gotta fucking save that too. That's crazy, man. Okay. Grab the first available platform. Use the first CPU device the platform divides. Create a context within that. Create a command queue to feed that device, okay? All right, this noob stuff goes away. Man, that's so fun saying the word noob. All right, what do we need to do? Get first available platform. Use the CPU device. Use CPU device. Create to feed device. Okay. Where the spam platform and order queues. Create buffer. Buffers for each. All right, that makes sense. Why do we put, what do we put in device memory? Just to see array, the contents of the buffer. Interesting. OpenCL. Hold your original host site data. Okay. What does this even look like? Exercises. Oh man, look at that, looks hard. Bro, are you serious? You want me to do this shit? Damn. Oh, this is super noob. I have to write all of this. Get platform IDs, man. Okay. All right, let's not complain. Let's just try it. Do we have something like CL? CL in. Wow, man. CL platform. Dude, this is gonna go crazy, man. Alright. CL get platform, right? See, what does this shit do? We want to grab the platform first. How many entries? How many platforms? Number of platforms. Man, I could not tell you, man. Zero null? What the fuck? Why are you doing that? Okay. Yeah, it looks ugly already, bro. Oh god. Look at that. No, I don't want to do C++ stuff. Okay. Mm-hmm. Why is this not even, it's not the fucking same, bro. Oh, like. Okay, there's no, okay, I don't think anyone actually writes this shit anymore, right? This is all like abstracted by other APIs. Alright, let's go to our NOOB steps. Create the context, define the platform. Why is it different stuff? Like, look at this. Let's just read it. Oh, right here, okay. Where's that shit? Oh, this thing, honestly, this is way better. I'm gonna start using this shit. All right. I don't quite understand why we're doing that. And I kind of do, but not really. So I'm just gonna fucking do something. Get available. I'm probably right. Client int number platforms. Number of entry. What the fuck? Okay. this goes error. And then what the fuck does error code do? Number of platform ID entries that can be added to platforms. ID entries that platforms did not know. This is just printf shit. Okay. Fine, dude. I'm gonna start using your shit. All right. Check error. What does it do? Check error, bro. Check error. Okay. Printf. No platforms found. Just fucking null, right? Null everything. File name. Finding. Bro, can I just do null? No, who gives a fuck? Unexpected. The argument is Clint, bro. Okay. Dude, are you using... Wow, we're really struggling on this, huh? You know, we don't even need that, honestly. Wait, file. No, I've never seen that before. Macros, okay, that's good. That's honestly pretty sick. Fuck. Will that make you happier, bro? Let's just not do that then. Oh my god, bro. Okay. NOOB, bro. Yes, I am a noob. That worked. Oh, it actually worked. Holy crap. It's kind of redundant, rather. What did this guy do? Check error. That's what I was trying to do, man. Check error. Right? Oh, is it? That's good. I'm gonna start doing that, man. That's cool. See, the more you learn to see shit. Finding number of platforms. Oh, dude. That's sick, bruh. Else town. Number of platforms. And then we'll just do this again, bro. Does that work? Found one platform. Get platform. Okay. Man. Okay. Honestly, I'm done with this. This one's shitty. I don't need you. Get device ID. Oh, first platform ID. See, I created some context within a single. What is he doing? I can't just do this in one. Get device ID. Get device ID. Okay. Get number of platforms available. It's an array of shit, right? What is it? Platforms. Am I spelling that right? It looks so wrong. How the fuck you do arrays, bro? See, this is bullshit. Oh, okay. Okay. I see. We're just getting a number of platforms. And then we're storing them in an array because we wanted to look at the devices in them. Okay. So if we're doing that, what the hell did he just use the first device? Okay. Okay. Hey, my poor wolves. I mean, they're not really my wolves because I'm not that big of an actual fan, but getting blown out, man. Rest in peace. Get device IDs. I don't get what the hell are they doing. Number of platforms. What the fuck? Get all the platforms. I'm like, dude, this just sounds. Okay. Get all platforms. I don't like that. I don't like that at all. Number. Nah, man. You're telling me of platform IDs that can be added? Number of entries. Why does it do it like that? Ah, that's terrible. I don't like. For some reason, I just don't like how you're using this twice. First, find a number, and then get all of them. Like, I don't know. Not a fan of that. Okay, we're doing complexity. I understand this shit. Explain normal entries, okay? I mean, why can't I just say that? Oh, okay. Oh my god. Yep, I'm stupid. Yeah, but like, that's crazy. That it uses that. Like, come on, man. Okay. And then it wants us to do this. Use the first device. Get GPU. Let's GPU device. Get device IDs. Platform ID. Device type, number of entries, devices, number of devices. Okay, let's just look into this some more. See, I got number of entries. That's wild, bro. Because we don't care about the number of devices. Okay, this might not work actually. That's a lot of work. Alright, actually I don't care. I just don't think anyone actually. This is. Oh, that's. Oh, this is all so ugly, dude. fuck did you want from me again? I'm pretty sure that's right, isn't it? Just getting fucking platform ID. Pretty sure that's right. Oh god. And it's not, I'm not gonna, no, I don't care about that. Platform. First platform. This is right, is it not? Is it just value that? Yep. Oh, this is wrong. Why is this wrong? Oh god, is it just because? What the fuck is this? Man, bro, my hair is all over the place. What the fuck is a P? Okay, this isn't even necessary. Yep, that was unnecessary. should just be a fucking 0. What the fuck? What the fuck? That's like not helpful at all for brother, what do you mean it's deprecated, man? It's not deprecated. Not on my watch, bro. Um, will you be mad? Okay, you're not mad. Alright, honestly, I'm getting hungry. So that's it for now. Alright. Goodbye, everyone.